our next speaker is Sabrina Pereira. And the talk is entitled Cryptographic Key Management for Spaceflight Software.
Perfect. Thank you so much. All right. Hello, everyone. My name is Sabrina Pereira. I'm a research engineer here at Southwest Research Institute, and I am part of one of our cybersecurity teams. And today I'll be talking about cryptographic key management for spaceflight software and how it relates to cybersecurity. So first, it is becoming increasingly evident that cybersecurity for satellites is very important. Space systems are critical to U.S. security, our economy, our work, our jobs, our life. And we have examples of what can go wrong. For example, the Russian cyber attack on the U.S. By satellites in Ukraine, which disabled thousands of modems using malware, widespread communications disruption. And there are multiple government initiatives towards increasing space security in the U.S. There's the proposed Satellite Cybersecurity Act, which is looking to provide resources for commercial satellite systems to increase their cybersecurity. There's a Department of Homeland Security working group looking into strategies that can be incorporated for the same goal. And the Department of Defense has a commercial space integration strategy looking to see how cybersecurity can be made more secure in the commercial solutions so that that can be incorporated into military defense systems. So all of this to say just some examples of how we know cybersecurity is important and is only going to be a bigger part of development on space flight systems. So what I want to do today is make clear how cryptographic key management is essential to cybersecurity and how basically it works. So cybersecurity relies on cryptographic algorithms. So we know encryption to protect the confidentiality of your data, digital signatures to make sure that the data has been produced by an authenticated source and that it hasn't been changed. All of these cryptographic algorithms and the keys that are used to sort of put a lock on your data to protect your data are using this key to, let's say, put this lock, and then a key on the receiving end to unlock it and receive that data and do something with it. So in that same analogy, having your cryptographic algorithms with badly managed keys is akin to having your lock with your key sitting right next to it, open for an attacker to just take that key, unlock the lock. It was like it was never there. So all that to say, key management is the backbone of cybersecurity. If we don't have key management, if we don't have secured keys, we don't have cybersecurity, regardless of how fancy our algorithms are or anything like that. So for today, an overview of what I want to go over, what is key management, and what are some relevant key management standards that exist, what they say about key infrastructures, and what are special considerations for space. How can we protect our cryptographic keys from exposure to attackers or generally attackers? And what are some areas of research that we are looking into and hope to look into? So for what is key management, I have this definition adapted from NIST. They are the activities involving the handling of cryptographic keys and other related key information during the entire life cycle of the keys, which includes the generation of these keys, the storage of the keys, the registration of the keys in the system, the usage of the keys, and the eventual destruction of these keys. So to go over how do we actually use these cryptographic keys, of course, we are using them to protect our data. We are using them in cryptographic algorithms. But there are two main categories of keys that I want to go over and distinctly differentiate. Symmetric keys and asymmetric keys. So symmetric keys are involved in operations with just one key. So you'll often see them used for encryption, where you use one key to encrypt your data and the same exact key to decrypt. They're also used for message authentication codes to prove that You can add a code to your message to make sure that the message hasn't been changed and it has been produced by someone with that key. On the other end, asymmetric keys, what they're widely used for are digital signatures that don't just prove the message hasn't been changed, but it will actually prove the identity of whoever wrote the message. And they can also be used for encryption, but because the operations are a lot more computationally expensive, they're usually used for key distribution, where a public key is used to encrypt a symmetric key and then decrypt it on the other side. So a couple different use cases, but they can be used for similar uses. These all together, these key types and the algorithms that can fit within these are all used for secure building blocks for communication. So that kind of covers use cases. In terms of the lifecycle side, I want to go over some lifecycle phases for what are the 4 main life cycles for keys. For all of these life cycles, it's important to have specific processes in place. So first cycle is pre-operational, where the key doesn't exist yet or hasn't been registered to the system. And for this, it's important to have the process to actually create the keys and make sure that they get to the correct devices. In the operational phase, this is the normal key usage that you'd expect, for example, encryption or digital signatures, used as essentially as you would expect them to use. In the post-operational phase, the keys are available, but only for processing. So what does that mean? This is whenever your keys may have been compromised, for example. So you know that a key is in the hands of an attacker, but you have some previous information that you still want to decrypt, for example. So you know that key is no longer going to be active. It's not going to be used for encryption anymore, and not going to be used for authenticating data, but it will be used for previous archived examples, for example, or anything like that. The other kind of similar case, when your key might not be compromised, but it may be as part of a policy, our keys are only used for 1 year, something like that, or our keys are only valid for 6 months. Our keys are valid for 5 years. This is all part of like a cybersecurity policy that you might put in place. And similar situation where you might have those keys archived to look at previous data, but you won't be using them anymore. And the final key lifecycle phase is destruction. So this means that the existence of the key is no longer available. The private key material is deleted. What there might be is metadata about the key, audit logs about the key, so its existence, the evidence of its existence, but not the private key material, so it will not be used. So yes, important to have processes in place for all of these parts of the life cycle. So that leads me into key management standards. So there are a variety of key management standards to help us figure out what we're supposed to do about all of those processes, making sure that all of our key management lifecycle is secure. So there are 2 standards that are the most, let's say, representative or most useful that I wanted to bring to light. So the first ones come from NIST. Now I'll go into these a little bit more detail in further slides, but the NIST standards are used across industry, gold standard. The CCSDS standards are more specific to space applications. So they take inspiration from the NIST standard and make it more applicable to space. So to go over the NIST standard and kind of what it does, and it has, it's a primary key management reference across industry. It's often referenced by other standards, including the CCSDS standards, and it provides guidance, best practices, and definitions for key management, which is very key to get a consensus on the definition for everything and have multiple industries, multiple groups be on the same page about what it is our goal is with key management. The big thing with these standards is that it has limitations for space applications. It doesn't have a large focus on resource-constrained devices. There's more of a focus on making sure that your security policy is as strict and stringent as you would want it to be, and then designing your systems to meet that level of high scrutiny. And that is very well and good, but hard to do sometimes. So for that reason, very clearly, there are CCSDS standards specifically adapted for space data systems. One big thing that they do not cover is secure key storage, and I'll come back to that, but it's just one differentiating factor. The 2 ones I wanted to bring up to that are good to note. The Space Missions Key Management Concept Green Book, the informational report. So this was released in 2011, a little bit older, but it provides a lot of cryptographic key management concepts conceptualized for space. A lot of the topics that are gone over in the NIST documents are kind of taken and more narrowed in to be more representative and useful for a space concept. On the other hand, the other document is a symmetric key management document, which is an actual recommended practice released back in December of 2023, so very recently. Now, this actual recommended practice has recommended key types, practices for communication security. So this one is more, instead of just definitions and ideas of architecture, it has that as well, but something more concrete to actually build off of. So I've looked over those, and I wanted to pull out some key ideas about the key infrastructures that these go over and what are some special considerations for space and these standards. So to go over first the key infrastructures, there's two big main types of key infrastructures. You've got your secret and symmetric key infrastructures and your public key infrastructures. And these relate directly to the key types that I mentioned before, where you have a single symmetric key and those associated algorithms, and then you have public-private key pair and the associated algorithms. So in a symmetric key infrastructure, your participants are going to be using the same key for secure communication. The big thing here is that it is very efficient. Those algorithms are very efficient. It's simple to deploy and use, but there are some limitations. So it's simple to give all of your devices the same key and have them set up for communication and things like that. But the big drawback is the distribution of the secret key material. You have to make sure that you have a secure channel from which you are distributing the secret key material. So that might be fine and well if you have all of your devices in front of you and you're injecting them with the same key, but if they're already fielded and they don't have the keys yet, or various different situations, that's something that can be quite difficult. It's also difficult to recover from a compromised key if an attacker were to expose one of these keys. All of the keys in all of the groups, they're all using the same key, so you have to replace every single instance of every key on all of your devices. And the other drawback is that a key can't be bound to an entity. Everyone in the group has the same key, so there's no concept of a separate key for a separate unit. On the other hand, public key infrastructure, the operations are a lot more resource intensive compared to symmetric, but it has those drawbacks that I mentioned for symmetric are not here. So key distribution is easily accomplished because of those key pairs, having the private key that you can just stay on your device, and then the public key that can be freely shared. In that same space, keys can have bound identities, and it is easy then, if there's a compromised key, to revoke it and tell everyone, beware of this key that has been compromised. So it's effective for those reasons. And for those reasons, that's what we use in our IT infrastructure and most everything that we use here. PKI is used for most infrastructures. So just to outline the pros and cons, secret key infrastructure, symmetric key, easy to deploy, great performance, but key distribution is a bit of an issue, and identity binding when needed is an issue. On the other hand, public key infrastructure, you've got simpler methods for key distribution, you've got identity binding, and ease of replication, but the large number of keys can be very complex to manage, and you've got performance drawbacks, I suppose. In resource-constrained environments that space-based systems have, symmetric key infrastructure should be leveraged, which makes sense as to why the CCSBS standard exists for symmetric key infrastructure. But there may be an opportunity to highlight the best of both worlds, I suppose. Now I'll go into how can we protect these cryptographic keys. So I pulled a couple of the best practices from NIST for key protection. There's two states that you can have your keys. They're either in transit, moving to their eventual destination, or they're at rest on the device where they will be used. So while in transit, secure transmission is the big thing there. There's two main methods of secure transmission. You've got your manual method, you've got your trusted courier that is injecting these keys in, or you've got some kind of automated key exchange protocol. The big thing there is that most of the automated key exchange protocols, these are based on asymmetric keys. So that's kind of a difficult thing for symmetric keys. In terms of availability, you want to make sure that this key will get to its eventual destination. So using redundant or multiple channels, error correction codes to make sure that gets to where it needs to get to is important. In terms of integrity, making sure that the key material isn't modified in any way, that it is as it should be, as it is registered. There are a couple cryptographic algorithms that can be used there to preserve the key integrity. And finally, confidentiality. Anytime the key is transported, should be encrypted in some way. Now, while at rest, the big thing is having the secure storage, having the keys contained within a cryptographic module and make them be easily available. There's no point in having the keys if the keys cannot be used, so it's important to have that key be available and not completely stall communication, cut off a device from the network. In terms of integrity, there should be limits on what processes are able to access stored key information. And again, there's cryptographic mechanisms to ensure that the key material has not changed. In terms of confidentiality, this one is a little bit difficult. So one thing that can be done is encrypting it and having some other key to decrypt it, or if a user is able to enter a password or something like that to decrypt, that can be done to be able to use the key material. The difficulty with standalone devices is there is not that element of being able to transmit. So there's this idea of, I need a key to decrypt my key, and so that key needs to be decrypted. And so at some point, there is a plain text key somewhere, unless you have a hardware physical protection mechanism. And that's one of the largest challenges, being able to implement something like that. So in terms of what hardware security devices for space systems look like today, as far as I can tell from all the publicly available research, not used widely, and that makes sense. Increased satellite weight, increased power usage. You can't just take whatever has been developed in other industries and just apply it to space. It's not going to work like that. It has to be specifically customized. And just in general, the thought of an attacker reaching this like very difficult to reach device and hijacking it is not something that's been at the forefront of minds in historical past. But as our technology continues to advance, it's going to be something that's going to be more important to pay attention to. And solutions will require merging knowledge from across industries, cryptography, hardware, astrophysics, just a lot of merging of different knowledge types to come up with solutions. So there are a couple key papers. There's Space HSM and Space TE, Trusted Execution Environments, that kind of go over this, that are interesting, if that is of interest to you, but not too many more that I could find. So I wanted to go over what hardware security devices kind of look like in other industries. And I myself am a little bit more familiar from the automotive perspective, so I'll have a little bit of a bias towards that. But hardware security modules, or HSMs, is what you usually hear of. It's kind of an umbrella term that applies to multiple hardware security devices, but usually what is meant by an HSM is a standalone device that can securely generate, store, manage cryptographic keys, and can be used for a large system. And the big thing there is that it's also tamper resistant. These are also tamper resistant, so if someone has physical access, they wouldn't be able to extract the key, even if they have physical access. In a similar fashion, the trusted platform modules tamper resistance is big for those too. They're generally more integrated for the device, so the cryptographic algorithms that are used for those are more device specific, but kind of in a similar, have a similar vein as HSMs. Now, what is interesting that has been done in the automotive industry, the secure hardware extensions, there is a need to create the lightest version of like an HSM type unit because of the resource-constrained nature of the electronic control units on the vehicles. They need to be as light as possible, as small as possible, and have as little as possible, essentially. So this standard has been written where cryptographic keys are protected from software attacks, which means that There is no software processes that have access to the key material. There is no extraction of the key material outside of this unit. If there were to be physical interaction, someone could remove the key physically, but there would be evidence that that was done. So this was created to be a very highly flexible, low-cost standard and way of securing your keys that could, something flexible that could be possibly be leveraged for space applications. And just to drive the point, some similarities between automotive and space that I wanted to bring up. They both have networks of components of differing and constrained resources, deal with components of varied network availability, and both require specialized communication protocols, which all require flexibility. You can't just, the traditional protocols that are used in IT infrastructure don't work well. And these two industries aren't, perfect alignment, but there is enough similarities to where there are lessons learned that can be applied and opportunities to take some lessons. So that'll just lead me to our areas for current and future research. So of course, I've talked about inspiration and adaptation from the automotive industry, specifically in the, I mentioned hardware security and the secure hardware extension, and that way of thinking around how do we do the most that we can in terms of cryptographic protection, but recognize our realities, and that kind of thinking. Another thing that we are looking into is how can we take what is good from public key infrastructure and symmetric key infrastructure and see if we can find an ideal balance that works for space systems and take what we've learned there. Another area that we are looking into is increased cybersecurity awareness. So leveraging the key infrastructure and having this network of keys for reporting cyber attacks and reporting attackers who might have access to keys and things like that, and get all that information to a command and control center that can then be able to act on that information. And finally, just to mention another thing that SwRI is looking into in a related space, implementing zero trust architectures on satellites, where if a module on a satellite might be compromised, it would not cause a compromise of the other modules on the satellite. And of course, behind that is a necessary need for secure key management. So that'll carry me all the way to the end of my presentation. In conclusion, cybersecurity and key management for space systems is of growing importance. The approaches that we take need to be adjusted for space. There are standards that begin to address this, specifically the CCSDS standards, and making sure that we are looking into ways of utilizing symmetric key cryptography, which is not something that is usually utilized, and seeing how we can bring that to its best potential. And finding realistic approaches for secure key storage. And then finally, there's multiple opportunities for advancing space cybersecurity research, and these are a couple of the things that we're working on. So thank you. That'll be it for my presentation.
Good. All right, go ahead. Yep.
Thanks, good talk. A couple of questions. Have you done any work or know of some papers that can do, that has done computational overhead that's needed to do PKI with symmetric keys?
So I have not worked on any. I do know of a couple of the ones that I mentioned. If you would like, I can send you some over. Yes, so the ones that I've seen have talked about, balance. There's not too many papers out there. There's not too much research that's been into it. But there are, I would say, 2 notable papers that I can send your way.
Okay. And the other one was on the HSMs. AWS, Gov Services, and a bunch of other cloud services provide HSM as a service. Do you think there is a possibility of using the HSM from the ground side, but a software-based key management on the spacecraft side?
I think it's something that has to be applied from multiple perspectives. So there does need to be from the ground side, a sort of HSM from everything on that side. The problem is the secure storage of any key material that is on the devices themselves. So it is layers upon layers. There's always incrementally better. But in terms of secure storage on the keys on a specific device, that is a individual device level problem to address.
All right. Question from online. Is CCSDS aligned with CNSA 1 and 2?
I'm afraid I don't know the answer to the...
Okay. Is there anything else?
The NIST and CCSDS, they were written a while back. I mean, NIST is updated regularly, but CCSDS is pretty old. Before GPU computing was really commercialized and definitely not in the space industry. So with GPU and soon, you know, some of the newer technologies, the quantum and whatnot, key breaking is going to become more feasible. Do you see any work in advancing standards to address the new computational methods, or are we still just waiting for that to become an issue?
So what I will say is that symmetric keys, so most of the symmetric key types that are, let's say, the best practice, AES keys, those are already quantum resistant. So from the symmetric side, AES keys, those are already, the problem comes more from asymmetric keys, the ones that are like breakable. So there is a lot of work going into quantum resistant algorithms in terms of the asymmetric keys. And there's NIST is putting out, or has already put out a call, and has been investigating which ones to standardize, which I would see in the next few years, I would expect them to have the list of the ones that we should use, something like that. But in terms of symmetric keys, AES is kind of the gold standard, and I expect it to stay.
Okay, and we'll do one last question from online. Are there any software-defined key storage mechanisms which could be used along with a software-defined CPU on a space-rated FPGA?
From my understanding, any software-defined solutions anything is better than nothing, but hardware will always be the true solution, because software will always be vulnerable to some extent, or able to be attacked to some extent.
Okay, thanks. Well, we'll have to answer the rest of the questions through Slack. Let's thank our speaker one more time. Thank you.